In the last lecture, what we have discussed some rings and some properties of the rings, and what I have given some exercises. So this video might be little bit lengthy, okay, because I'll have to cover this uh, many things, and also this video might be little bit lengthy. That's it. The previous lectures were about 50 minutes, and this lecture might be of 2 hours and 2 to 2.5 hours, okay. So that's all, and let's see how much I can cover. And yeah, this is the this is this is the seventh lecture, right? This is the seventh lecture of the ring theory, and what I have told in the last lecture. So in the last lecture we have discussed some, I give some exercises. I wish you everybody has complete these exercises. And yeah, I'm one of the exercise was that some of the exercise was you try to show, suppose if you have the zero divisor of a ring, this R cross zero divisor R and SB2 ring structure, and this I told you to verify these are not same, right? So I wish you have, and in fact you just have to show that Z of R cross Z of S is contained in Z of R cross S, and this is not equal, right? This is properly contained. So that's, and this is easy to show. You just take any element here, you just show this is over here, okay. So that's it. And what else? Now today I am going to start a new topic. It's called the characteristic of a ring. This from, okay, it's called a characteristics of a ring. What is it? So let me define characteristic of a ring. Yeah, it's called characteristic of a ring, okay. What is that? Let R plus dot be a ring. We say R has a characteristic n. This is positive integer, okay. This is from natural number. If n is the smallest positive integer, satisfying n dot a, this is 0. 0 means the additive identity 0, okay. That means you are adding n times to a, the minimum times that you get, the minimum times you operate, and you get 0, okay. That gives the characteristic of a ring, okay. This should satisfy for every a inside the ring R, right? For this should satisfy for every element a. This, it can be any element inside the ring R, right? So it can be anything. So we say this R has characteristic n, okay. So what are the examples? Some examples are given by something. Suppose you have a ring Q, ring of rational number. What is the characteristic? Can you find for Q? Suppose Q are the elements for P by Q, where Q is not equal to 0 and P by Q are. So can you find any positive integer n here such that this will give you the 0? Can you find here? You should be able to find a Okay, one more thing I have to show. Okay, that's it. So n and as usual multiplication is that p by q is 0 except n is 0. So okay, let me for before let me define. If just a second. Okay, just I'll have to mention one more thing here. If no such n exist, this implies characteristic the ring is 0. Okay, if there is any such n exists, then we can say the characteristic is n, otherwise we say the characteristic is 0. Now come to the example. Suppose you have q. What is the characteristic of it? Can you find any natural number in here such that this is 0 except 0? Or can you find any p by q n times such that it will give you 0? No. So the characteristic is 0. Similarly for r, this is 0. Similarly for c, this is 0. You cannot find any positive integer n such that this will satisfy. Okay, characteristic of z is also 0. Can you find any in here such that this will any any integer this will give you 0? So you cannot find here, right? So in Zn, what is the characteristic in Zn? Zn means suppose you have Z4. What is Z4? Z4 is 0, 1, 2, 3, right? So suppose Z4, you have Z4. So can you find any element here? This is such that all the elements will be 0. Suppose if you have any n and any a, this will be give you 0 for every a inside the ring R, ring Z4. So if you take n to be 4, okay, so 4 into 0, this is 0 is 0. Okay, 4 into 1, this is 4 means is 0 in Z4. 4 into 2, 4 into 2 means 8 is 0 in Z4, because you are dividing 8 by 4 and the remainder is 0. 4 into 3, 12 is 0 in Z4. So this ring has characteristic for any n, this ring has characteristic n, right? These are some examples. So suppose for in R, why this R has a characteristic 0? Why? Suppose you have a number n here and you have a here, this is 0. Okay, can you find any number n such that for every a inside R it will accept 0? You cannot find, right? So this is why, that's why the such n is not existing here. That's why this ring has characteristic 0. Similarly for that, similarly for that. Okay, understood? Okay, I'm asking you one question here, just try to answer. Okay, question, I will ask question anyway. Okay, example of an infinite ring with finite characteristic. Can you give me an example of a infinite ring with finite characteristic? Char means characteristic. Okay, here I am using the short version. So can you give me an example of infinite ring with the finite characteristic? So think this question, I will answer this question I'll anyway answer, but you just try to think in yourself. Okay, this kind of example or this kind of question can ask in your interview. Okay, so what is the, can you find, are you, so what will be that? So can you take any example of you just take, you take the infinite copies of z2. What is z2? z2 is 0 1, right? You just take the copy, that means the product of z2's sorry z2, how many times? The infinite product. Okay, infinite product of z2, that means you take z2 cross z2 cross z2 cross dot 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 dot, dot infinite product. Okay, you have chosen the infinite product. So what will be the characteristic for that? This is a ring, right? This is a ring. What is that? This is the infinite. So what are the elements of this? So each element has two choices, either 0 or 1. Each has two choices, either 0 or 1. So see, either it can be something zeros and 1. It will be some sequence of some 0 1 or something. Okay, that's, so what will be the characteristic for that? Suppose you have any element, it will be, of course it will be either 0 or 1. This is a tuple, right? Some a b c dot 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 dot. These are some tuple, infinite tuple, right? So this a and b, a b c's have two choice, either it can be 1 or can be 0, because every z2's has two choice, either 0 and 1, right? So if you multiply by 2 in any, either it can be 0 or it can be 1, it can be, so whatever, either 0 or 1. So what will be that? It will be 0 2, this will be anyway 0 na in z2. If you multiply by 2, it will be multiple of 2. It will, if this position is 0, then it will be anyway 0, and it will be 2. It is 1, so it will be 2 multiplied by 2 is 2. So in 2, z2 2 is 0 na. In z2 there is no 2, right? z2 2 is 0 na. If we divide 2 by 2, that will give you the remainder 0, right? So that's the idea here. So this ring has characteristic 2. This is the infinite ring, this has characteristic finite. 2 is a finite quantity, right? So this is an example. A similar way you can find in the similar can you example of infinite field with finite characteristic. This kind of question might ask in your interview. Okay, so that's the idea behind it. So this is time to prove some important top theorems, not theorem. Let me just think what I have to taught today. There is many topics here, so let me write something here. You know Zn, right? Zn addition modulo n multiplication modulo n is a ring, right? It is a commutative ring with unity whenever n is greater than or equal to 2, right? CRU, that means commutative ring with unity. You know what is commutative ring with unity? This is commutative and this has a unit element, right? So it is a field. Whenever when Zn is a field, it is a field, F-I-E-L-D, field, if and only if it is a division ring. Okay, I have defined it earlier. What is the definition of a division ring? That every non-zero element is a unit. Every non-zero element is a unit, right? If and only if n minus 1. Okay, are you getting my point? Every non-zero element is a unit. What does it mean? total element in Zn, total element is n, and every non-zero element we accept 1, you are eliminating 1. Okay, so total unit is phi n, and phi n is n minus 1. Okay, that's why I am writing here phi n is n minus 1. Every non-zero element is a unit. I am excluding the zero element here. So total n elements minus 1 element, that means 0 element I am excluding, n minus 1, right? So in every n minus 1 is a n minus 1 element is a unit. That means the unit is divided by phi n is equals to phi n, and this is n minus 1, right? Are you getting my point? I think you should get, because I have defined many things in earlier videos, and I think you should get. Otherwise, I will assume you are not studying well. So anyways, so if and only if n is prime, when n is n minus 1, phi of n is n minus 1, if and only if n is p prime. Okay, phi n equals to n minus 1 when it happens only if when p is p minus 1, sorry, n is equals to p prime. When n equals to prime, that means we are in Zp. So Zp is an integral domain if and only if Zn addition modulo n is an integral domain. Are you getting my point? Whatever I am writing the points, are you getting? It is a field if and only if it is a division ring. You know, this is the definition. Division ring means every non-zero element is unit, right? That's it. And every non-zero element is unit. Total element is n. Every non-zero element, that means I am excluding 0. So I am subtracting one element, n minus 1. That means what are total number of units is phi n, and I am removing 1, then phi n is n minus 1. When phi n is n minus 1, whenever n is prime, p is prime. So if p is prime, so Zn is an integral domain, Zp is an integral domain, na? So I think the equalities, the implications are clear to everyone, right? I think. Okay, so now a finite integral domain is a field, we know, right? Finite integral domain is a field. We have also proved in the class, right? What else? I will prove one theorem here. Characteristic of an integral domain is either 0 or prime. Okay, this is as a theorem or proposition. Proof. I know my handwriting is very bad, but I think you are able to understand, because I am writing also I am speaking, right? It should be clear. So anyways, so either characteristic of a integral domain is either 0 or a prime number. How will you prove? Suppose characteristic of an suppose R be an integral domain, right? Let us assume, suppose R be an integral domain. So I have to show R has the characteristic of R is either 0 or a prime number. Okay, if characteristic of R is 0, then I am done, because either 0 or prime I have to show. Suppose let characteristic of R, that means this integral domain is M, and M is not a prime, suppose. So if M is not a prime, so M can be M can be written as the multiple of two distinct primes, distinct primes, not two distinct primes, right? Suppose if M can be written as some M1 into M2, right? So M is not a prime, right? Suppose, towards the contradiction I am going to prove. Suppose M is m1 m2, m1 into m2, right? That means if m is not a prime, so m can be written as some m1 into m2. That means if m is not a prime, so m is a, what it says, composite number, right? M is a composite number, so m can be written as some m1 m2, right? So where 1 is less than m1 comma m2 is less than m, right? Where m1 and m2s are in this interval, okay, of course. So since m is an characteristic of a ring is m, so we can, what we can do, so we can write, since this, so this will imply that ma equals to 0 for every a inside the integral domain R. It's not it, because the characteristic is m, so m a, this is 0 for every element inside the ring or the integral domain R, right? So m can be written as m1 m2 a, this is 0 for every a inside R, right? What does it mean? You can write it as m1, and what is m2? m2 you can write is a plus dot 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 plus a. How many times? m2 times, because I am assuming this m2 times, right? This is 0, is not it? Are you getting my point or not? Okay, that's, yeah, this is actually m1 m2 of a, this is 0, right? This is 0, right? It's not it. What does it mean? This means that m1 m2 a, this is 0, right? It's not it. This is 0, right? Oh my god, yeah. So this is 0. So if it is 0, so what does it mean? Either m1 is 0 or m2a is 0. So m1 is 0 is not possible. If m1 is 0, then the entire quantity will be 0. This will be 0, because m1 is into m2, that if m1 is 0, the entire quantity is 0, and we have assumed that this is in 0 case. We have already assumed that we have you assume that this is already greater than 0, right? This is already greater than 0, so m1 cannot be 0. So I will, so if it is not 0, so this has to be equals to 0. This means that m2 of a, this has to be equals to 0, okay? What does it mean? m2 of a, if m2 of a is 0, this is going to be a contradiction to the fact that m is a characteristic of the ring, because see, m is the characteristic means m is the smallest positive integer such that ma, this is 0, right? But we are getting m2 which is lesser than m, still it is giving us 0. Are you getting my point? I have assumed that m is a characteristic of ring or the integral domain R, and I am getting that m2 which is smaller than m, still it is giving us m2 dot a is 0. That means it is contradicting to the fact that m is a characteristic of the ring, okay? So this is a contradiction to the fact that m is a characteristic of the ring. So that's why m has to be a prime number. There is no other choice in our hand other than that. This has to be is a prime number. Otherwise, if you not a prime, this is composite number, so you can write into the format m1 m2. Suppose, are you getting the proof? m1 m2 0, that means one of them has to be 0, because m1 m2 of a, what does it mean? From here, how can I say? Because in integral domain, what we are in an integral domain, right? So there is no zero divisor. See here, one might ask one question here. So m1 m2 m1 and m2a is 0. How can it imply that m1 is 0 or m2a of 0? Because you are in an integral domain. Integral domain, there is no zero divisor, so one must have to be 0. Okay, so that's why you are in an integral domain, right? You are in integral domain, so you cannot say that m1 is non-zero, m2 is non-zero, still I was giving a 0, because you are in an integral domain. So it must have to imply that one of them has to be equals to 0. There is no other choice in our hand, right? So this is m1 is 0 or m2 of a is 0, right? See, if m1 is 0, the entire quantity will be 0 here, m1 into m2. If m1 is 0, the entire quantity will be 0, the characteristic ring will be 0. But we have already assumed that m1 m2, that means m, this is greater than 0, strictly greater than 0, right? So that's what m2a is 0. But if m2a is 0, then what is the meaning of the characteristic of a ring M? Because m is the smallest positive integer which is giving you m dot a is 0. But we are getting that m2 is strictly lesser than m, but still we are getting that m2a is 0. This is the contradiction to the fact, right? So m has to be a prime number. I think you get the proof, because this is really not a hard proof. This is very easy and very formal proof here, right? So that's what. So now let's move on to the another thing that I want to mention. So if R is a ring with unity, okay, so what can you say about in the characteristic? Okay, so let me just recall what I have to teach. If I assume that R is a finite, so anyways, so let's move to a question here. If R is a ring with unity, if R is a ring with unity, then the first proposition is if. So ring with unity means there is a 1, right? There is a 1, right? That means if I can say order of 1 is less than infinity in the group R plus. R plus should be a group, right? So I can talk about the order of 1, right? 1 is an element, because ring with unity, that means 1 is an element inside the R. And I can talk about the group, since R plus is a group, so I can talk about the group, I can talk about the order of 1, right, in the group R plus. This will imply that characteristic of ring R is order of 1. If order of 1 is finite, then the characteristic of ring is order of 1. And the secondly, I will prove one more, if order of 1 is infinite, that means you cannot find any positive integer, smallest positive integer in such that this will give you the identity element, that means the order of 1 in the group R plus, it will give us the characteristic of ring is 0. And this is, I think this is clear. This should be clear, because if you cannot find any positive integer n such that n dot 1, this is the additive group 0, so you cannot find, so you must have the characteristic of R is 0, right? Because you cannot find any here such that n, what do you mean by n time 1? N time 1 means 1 plus 1 plus dot plus 1. That means you are adding 1 n times. This should give you 0, but this is not giving you 0. So this, what does it mean? The equivalent meaning, the characteristic. So that's why. So this is easy. The second one is easy, clear, right? This should be clear. And the first one I am going to prove. Okay, suppose that order of 1 finite. Okay, order of 1 is finite. Suppose order of 1 is k, which is finite, and characteristic of R is m. My claim is not equals. My claim is m equals k or k equals m. How can I proceed that for that? So first of all, you need to, m is the characteristic of a ring, right? So what you can, so m is the characteristic of a ring. So m is characteristic of R is m. What does it mean? This implies that m dot 1 is also 0, m dot a is 0. That means in particular m dot 1 is 0. What does it mean? What does it mean? M dot 1 is 0. That means m into 1 is 0. That means m is the smallest positive. M is the, so m is the integer for which it is giving you the identity element. But can you say that m is the order of 1? You cannot say, right? Why you cannot say? Because m might not be the smallest one. There might be a positive integer which is strictly lesser than m, and still it is giving you 0. So the best thing you can say is the order of 1 should divide m, right? It's not it. You just tell me, is it? It's not it. This implies, what is order of 1? Order of 1 is k. K divides m. This is number 1. That means number 1 or number a. Suppose number a. Suppose this is number a. Equation number a. Right? K divides m. Okay. Now, since k, what is k? Order of 1 is k. Right? So k dot 1 is also 0, right? Okay, if k divides m, how can you say? What can you say? If k is dividing m, that means m by k is a finite quantity. Is finite quantity. That means positive integer, right? It's an integer actually. Integer. Okay, m by k is an integer. So m is dividing. See, m is a positive integer, k is also a positive integer, right? So this is a positive integer, this will be positive integer. So can't you see that k is less than or equals to m? M is bigger, right? Of course m is bigger, because if m is bigger than if k, then you will get a positive integer here, because m is also positive, k is also positive, right? So that's the idea here. So this is a, suppose this is a, right? So characteristic. Now what can you say about, how can you proceed for the other part? Okay, you have to show that k is less than or equals to okay. So my claim is m equals to k. Anyone have any idea here? So m is, so k is less than or equals to m. I have to show that m is less than or equals to k. So k is less than or equals to m. Okay, so see, if m dot 1, so okay, see, order of 1 is k. So order of 1 is k means 1 plus 1 plus dot plus 1. this is equals to 0. This is k times. What does it mean? K times, because the order of 1 is k. The k times you are multiplying, you are adding. This should give you the additive identity 0. What does it mean? It means k dot 1. This is 0. What does it mean if k dot 1 is 0? See, m is the smallest positive integer for which m is the smallest positive integer for which m dot 1 is 0. But we are getting another k which is less than m. Still it is getting that k dot 1 is 0. What does it mean? Just a second. Yeah. What does it mean? Can't you see that k dot 1 is 0? This means that m is less than or equals to k. Since m is the smallest natural number, that means the characteristic of m, characteristic of r is m. Am I clear with you? Anyone has any doubt here? See, k dot 1 is 0. Up to this is okay. So why m is k is greater than or equals to? See here, because m is the characteristic of a ring, characteristic of the ring. So m dot 1 is, so m dot 1 is 0. Also we are getting that k dot 1 is 0, and m is the smallest positive integer for which that, but we are getting a k which is smaller than m, and we are getting that k dot 1 is 0. That essentially means that m is less than or equals to k. This is b. Suppose from a and b implies that m equals to k. Are you getting the proof? My proof? m is equals k. Are you getting my proof here? K dot 1 is 0, right? So what does it mean? That m is less than or equals to k, na? M dot 1 is 0 and also k dot 1 is 0. Okay, so m dot 1 is 0. That essentially implies that k is less than or equals to m, and k dot 1 is 0. It essentially implies that m is less than or equals to k. That means that m is equals to k. That's done. So what we have proved? So if R is any ring with unity, then if order of 1 is finite, then that order of 1 will be the characteristic of the ring. Example you are getting. So in Zn, suppose in Z5, the order of 1 is 5, and this is also the characteristic of Z5. Okay, characteristic of Z5. Okay, so I think okay, now what should I do? This is over. Oh my god, why the mosquitoes are disturbing me, right? Okay, so this is so if R be a ring with unity, so we can say that the order of 1 will be, if order of 1 is finite, then order of 1 will be the characteristic of the ring R. Okay, so one more thing here, if R be a finite integral domain, what does it mean? That order of this R, finite integral domain, is a field, right? Some p power k, for some p is a prime and k is whatever, so p is prime, right? P power k. That means p dot a is 0 for every a inside ring R. What does it mean? This implies that order of a divides p in R plus. So cardinality of field cannot be divisible by two distinct primes. Cardinality of R, if it is a finite integral domain, so cardinality of this field cannot be divisible by two distinct primes. Why? So if it is an integral domain, so order of R will be some p power k. Okay, so what do you mean by the p power k, right? It's not it. Are you getting my point? It's not. Are you getting my point? If R is a finite integral domain, what does it mean? Order of R will be some p power k. This is a finite integral domain. This is, suppose some zp is okay, some p power k. So p dot 1 will be 0. P dot 1 will be 0 for every r, because the characteristic of the ring will be p, right? The p dot a p, the characteristic of the of this integral domain, the characteristic of the integral domain is p, right? So order of A will be divided p in r plus. Okay, so cardinality of a field cannot be divisible by two distinct primes, because p is a prime, itself a prime, and it cannot be divisible by two distinct primes, right? Order of 1 divides p. So okay, that's the this is over, I guess, and I am going to introduce a new notion which is called ideals. This is the most important topics and important topic. Okay, these are called, what this call is ideal. This is important, right? Whatever we have discussed, these are some basic ideas. So now from now on it is little bit conceptual, right? But what is ideal? So I think let me just motivate behind it. So what we have discussed in the earlier lectures, okay, so you are in group ring theory course, so you must have done group theory, right? So what is the definition of a normal subgroup in the group? Exactly the same role will be played by the ideal in the ring theory. Okay, the notion of normal subgroup you have defined, right? And the coset you have defined, and the normal subgroup if and only left and right cosets are equal. So similar role will be played by this ideal in ring theory, the entire ring theory course, right? The ideal is a very very important topic, same as the normal subgroup is very. If you can encounter the ideal, you can solve many kind of questions, whatever. So if you definitely have to encounter the if you can see the ideal, that's it. Okay, so let me define what is ideal. So same as the normal subgroup will be the same role as the normal subgroup will be played by the ideal, right? So suppose R be a ring, let R be a ring, and is I is a subset of R, and I is non-empty, right? We say I is left ideal if A minus B inside I for every A comma B inside I, and R dot A is inside I for every R inside the ring R and A inside I. That is, Ri is contained in I, okay, for every R. Okay, so R be a ring, and if A minus B, that A minus B means A with the additive inverse B, A minus B is inside I, and also R dot I am multiplying by in the left side. This is left, this is right, right? So R is the left side, so that's why this is called left ideal. Okay, So because that is why I am multiplying r by in the left side. This is called left ideal. So similarly you can define the similar way you can define the right ideal. So right ideal, I is right ideal if a minus b inside I for every a comma b inside I, and I know you predict what I am going to do. A dot r, I am multiplying r in the right side, is in I for every r inside r and a inside I, right? Actually this is called IR is contained in I. This is called a right ideal, and this, okay, this is important. I think the definition is clear to everyone, right? Okay, the definition is clear to everyone. So this is right ideal and left ideal, and we say left and right ideals are both actually is called ideal. Left ideal plus right ideal, we say ideal. Left ideal plus right ideal is equals to ideal. That means we say I is an ideal if it is a left ideal as well as a right ideal. Okay, so if I say the I is an ideal, you have to assume that it is a left ideal as well as a right ideal. That's it, right? So one thing, verify right now, verify left and right ideals are both subrings of R. Right ideals are both subrings of R. Verify, just verify. I'm coming in 1 minute. Just a second. Just the mosquitoes are really embarrassing. Just let me just give 1 minute, and you just verify it. I think it should be okay, huh? Yeah. So, oh my god, what happened here? Just a second. What happened here? I don't know. Yeah. Okay, so have you verified left and right ideals? Just use the definition of left definition of subring, and what is the left ideal and what is the right ideal. Just use the definition. I think it should be clear to you. Okay, this is very easy to show. I satisfies two properties here, right? What are the properties? So I'm giving you a sketch here. So what is I? I satisfies a minus b should be in I, and ri should be inside I, and r is inside r, and a comma b is inside I. So this is easy. You have to show that you just have to show the every element in that satisfying both are as a subring. It will going to be subring. What is the condition for a subring? You know it very well, so I'm not going to prove, right? So anyways, I'm going in some examples. What are the examples? So examples. Examples are, suppose 2z is a ring, right? Sorry, z is a ring, right? So you know 2z. Okay, the notation of ideal, notation for ideal. So you have written as a normal subgroup whatever, and the same similar notation is here. I is an ideal of R. This is the notation. Example, suppose example. So Z, you know, the suppose that your ring is Z. Now what are the ideals? Is 2Z, is there ideal in Z? Let me verify. So first you have to show that A minus B should be into Z. What do you mean by A minus B? So if you for every A comma B inside 2Z, so this is very clear. This is very clear. Suppose you have some 2K and you have some 2M. This is of course inside 2Z, right? So first condition is trivially satisfied. So what is the next condition? You have to show that R dot 2Z is contained in 2Z. It's not it. And 2Z dot R is contained in 2Z, and R will vary for all R will be vary in entire Z. This is also trivial. So if you multiply R is, you already have multiple of 2k, and you are multiplying any R here, so it is obviously a multiple of 2 na, obviously some 2m, right? Some for some m, so that's it. This is also clear, this is also clear. So 2z is a subring of Z. Okay, just so the zero element, that means the trivial rings are trivial ideal 0 and R itself. Are trivial example of ideal in R. Trivial example, right? So this is clear, I guess. What are the examples? So let me define some abstract examples. So example 2, this is sub example 1. Suppose, so you know the zx, right? What is zx? Zx is all those polynomials px such that coefficient of p are integer, right? This is an this is a ring, right? In fact, this is a CRU. Verify. If you cannot see, verify it. Okay, so I'm defining an I here. You have to check whether this I is going to be an ideal or not. All those px inside the ring zx, that means I am collecting all the polynomials from the ring Z such that p of 0 is 0. Is it ideal in zx? Ideal of zx? Okay, can you what do you think? Think it. I'm giving you exactly 1 minute and just think it. I'm giving you 1 minute here. Think it. So just let me. Think it. Okay. Okay, I think the time is over, right? Okay. Oh, is it ideal? So for ideal, what you have to check, you just verify with the definition, that's it. And I think it is very easy to verify whether this is going to be an ideal or not. Suppose, so let me do one example is very formally. I'm doing this example very formally. How whether it is going to be an ideal or not. Suppose P and Q, suppose two member of this I. Suppose P and Q are two member in I. So that means P of 0 is 0 equals to Q of 0. Is not it? I have to show P minus Q inside. P minus Q is inside I. So for that I have to show that P minus Q at point 0 is going to 0. So P minus Q, what is happening? P minus Q at 0, which is actually P0 minus Q0, right? Which is actually 0. So this implies that P minus Q is inside I, because P minus Q is a polynomial. At 0 it is going to 0, it is giving us 0. That's why. So just a second, what is happening here? Yeah, it is fine. So P minus Q is I, and now you'll have to show that if you have this Rx, let Rx is a polynomial in Zx. Rx you have to pick from Zx, right? And you have to show that R dot P at x at dot P at 0 is going to 0. That's it. So R dot P at 0, which is just R0 into P0, and P0 is 0, R0 is whatever R0 is a finite quantity, and P0 is 0, this is giving 0. What does it mean? That R dot P inside I. Okay, similarly, what you can show, P dot R at 0, what does it mean? P0 into R0. What does it mean? 0. This means that P dot R is also in I. That means that this means that this I is an ideal in Zx. Okay, I is an ideal in Zx. Okay, so I'm giving you one more. So let me clear one thing. I will spend enough time in this ideal portion, right? So that's my intention. So anyways, so I'm giving you one more example here. What will be the example? Example 3. What is that? Suppose RB, suppose this is a matrix thing I'm considering. Suppose some A, B, C, D, you know, such that A, B, C, D are inside from Z. This is actually what is called is M to Z, right? 2 cross 2 matrices over integer. So I am giving you two ideals here. Whether they are ideal or not, you have to check. I am giving you two set here, two subsets of this R, A, B, 0, 0, such that A comma B is inside Z is a R, right? Is a subset of R, and I2 A, B, 0, 0, A comma B inside Z is a subset of R. You have to check whether I1 and I2 are the ideals of M to Z of R or okay. So check for the ideal. I am giving you 2 minutes. Whether both of them are ideal or one of them are ideal, whichever, you just check it. I am giving you 2 minutes here. I'm giving you 2 minutes here. After that I will start. Okay, so try it by the definition, just go with the definition, nothing else is needed here. Just go through the definition, what the definition I have just told. I just defined of the ideal. So the associated with a minus b should be in a minus b should be in I, and also the ri and ir is should be inside I. For every r inside I, r and I. So anyways, so you just take, I'm giving you 1 minute is lifting out. So this is very easy to observe, or this is very easy to verify. I think it should not take more than 2 minutes to verify. In fact, okay, the time is over. Okay, yes. So I wish everybody should have done this, and I think you should have done this. So for I1, check for I1. I'm checking for I1. I'm checking for I1, and you just check for I2, and it's a similar process will work here. This is 0 0, right? So anyways, so for I1, suppose a comma b to element in I1. So a comma b will be some look like some a1 b1 and some a2 b2. So definitely a minus b will be in I1. It is very clear. A minus b will be in I1. It is very clear. It is very obvious that, right? So, and you just need to verify that the second property, whether the left ideal or the right ideal. Suppose C be an element inside R and A be an element inside I1. So C dot A, I am C multiplying in the left side. I am looking for the left ideal. So what is C? Suppose C will be something like, because C will contain every element A, B, C, D, right? So I can take A, B, C, D here, right? And also, and for A I can take A1, A2 you can take A1, A2, 0, 0, suppose not, this is right. So what is that? A1, 0. So this will be A1. This will be A1, A2. So A2. This will be A1C, A1C. This will be an A2C. Is this inside I? Is this inside I1? It is not inside I1, because for I1 you will have to just this and this has to be 0, but this is not 0. So this is not left ideal. Right? Left, I am multiplying by left, it is not working. And I check for the right ideal. Suppose a dot c, I'm c writing in the from the live side, right side. What is the best thing I can do is a1 a2 0 0 s into a b c d. What is that? This and this 2 will be 0 0, and there will be some non-zero quantity. So this is inside I1. Clear? So this implies that right ideal. So this is not an ideal. So this is right ideal, and you check it. This will be left ideal. This will be left ideal, right? So ideals has been, so check for the ideals. So this is over, I guess, right? So can you let me ask some question right now? These are some examples, right? Now we have to say some example or some question. Let me see some questions, right? So let's see whether we can find or not. So I'm writing a problem. You just see the problem, right? These are from Einstein algebra. So I'm writing this question, right? Okay, so this question I'm writing here. Let me choose a color. This color is okay, I guess. So this question is of Einstein algebra, and this question has been asked in CSI Net September 2022. Anyways, so question. So let R be a ring and N be the set of all importance of R. And in all nilpotents of the ring R. Okay, that means N is a set. Suppose that N is a set. It is defined in this way: X all the elements of R such that x to the power n is 0 for some n inside n, right? So then option A n is an ideal in R. What is doing? This board is really not suitable. Option B, n is never an ideal in R. Option C, I don't know. Option if R is a commutative, then n is not an ideal. R is commutative, then n is not an ideal. And the option D, if R is commutative, then n is an n is an ideal. Which of the following is or are true? This is option A, this is option B, this is option C, this is option D. Right? Which of the following is or are true? This question has been asked in the CSI net September 2022, and this is actually the is of June session, but this has been the exam was held in the September 2022, and this problem was inside in the book of Einstein algebra. So anyways, so how much time it can take to solve this question? And this is little bit yeah, this is easy problem. This is easy problem. So you just have to think what is given by n is given, right? What is n? N is given by that all those x inside R such that x to the power n is 0, right? So you have to show whether n is an ideal or n is never an ideal, or if R is commutative then n is ideal, or whether R is not commutative then n is ideal or not. You just have to verify whether n is. Can you check for the ideal in n? So let me check. So I don't know what is happening with me, I don't know, but just take 1 minute, just give me 1 minute, and I think my board has been just a second. Just I don't know what this board is. Just a second. My god. Yeah, just a second. It's been, I guess. This is the question, right? Sorry for being. What is happening? Zoom in option plus plus sign option. Okay. I need some more space, more zoom option. Oh my god. Just a second. It was about something 89%. One 44% is zooming, right? Yeah, I guess this is. I guess this is okay. Yeah, and also. Okay, sorry for being sorry for this inconvenience. I don't know what is happening with my board, and I think I have to what some new. I have to think. Okay, so n is in what we have to check. What is that? What is that? I am not getting here. Yeah, colors are also being. Sorry for the inconvenience. So have to check whether n is ideal or not, and when n can be let. So let a comma b. I have taken two elements a comma b inside n. This implies that a key power n some n1, this is 0. This is some a key power b key power n2. Because see all the elements some okay for some n. Okay, so a to the power n1 is 0 because a is a nilpotent element, b is also a nilpotent element. Okay, so a to the power n1 will be some 0 and b to the power n2 will be some 0. Okay, by the definition, right? So can you think of what can you say about a minus b? Can you find any n such that this is 0? If you can find, then you are done. That means not done. That means you will be able to see the first property satisfying. But before that, you have to check whether a minus b to the power n is 0 or not. Suppose a key power b is a to the power n is 0. Not suppose, you just what is that? This is actually summation. What do you mean by this? N choose k, a key power k, b key power n into minus 1 to the power k. Is not it? And k is from 0 to n. This is the definition of to the 8 binomial expansion of a minus b to the power whole to the power n. That's it, right? You know. So for some n, so n is this. So can you find any n here so that a minus b? So this is actually nothing but you can write it is an in this term. So n choose 0, b key power n minus n choose 1, a b key power n minus 1 plus n choose 2, a square b key power n minus 2 plus dot 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 plus n choose n a की power n. Okay, this is right. So choose n, which is actually n1 n2, n1 into n2. For that, if you choose n1 n2, suppose if you have chosen n1 n2, okay, n equals to n1 n2. So see, b की power n, b की power n, n1, so you can write it as n choose 0, b की power n1 n2, but b की power n2 to the power n1 you can choose, b की power n2 to the power n1 you can write, also write b की power n2 to the power n1 n1. So this will give you 0. Come to this, so you are getting that a की power n1 n2 minus 1, right? So all those you have to see here. The coefficients are fixed, so I am not worrying about the coefficient, right? So whatever it is related, I am not worrying about the coefficient. So I just want to say the b to the power, whether b to the power n minus a b to the power n minus 1 plus a square b की power n minus 2 plus dot 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 plus a to the power n, whether this is going to be 0 or not, because the coefficient are anyway non-zero. Okay, I have to show this is 0. So b की power n1 means you can write it b की power n2 to the power n1 minus a b to the power n1 n2 minus 1. Is it? Is not it? See, b की power n1 n2 minus 1 will be something lesser than something which is less than n, right? So the power n1 n2 will be give you 0 here, plus similar a square b की power n1 n2 minus 1, this will give you this is 0, sorry, minus 2, this will give you this is 0, and this will be anyway 0. So all the term will be 0. Okay, all the term will be 0. This is 0, minus 0, plus 0, 0. So this will be 0, right? Are you getting my point? Whatever I am going to say. So this is going to be the first property satisfying, that a minus b is inside n. Okay, so now we'll have to check whether this is the right ideal or left ideal, right? How will you check for the left ideal and the right ideal? Oh my god. So let x be any arbitrary element of the nilpotent set of nilpotent, r be any is r, right? So what does it mean? This means that there exists k natural number such that x की power k is 0. Is not it? Are you getting my point? Because n is an element of this, and this is the set of all nilpotents, right? So this is 0, right? So what it x r to the power k and rx to the power k, what is that? So this is xr dot 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 xr. See, suppose if you assume that this is commutative, so you can write it x, this is k times, right? K times, so it will be x की power k, r की power k. If you assume that this r is commutative, so this is going to be 0, because x की power k is 0. Similarly for here, rx dot 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 rx, this is k times, this is actually r की power k, x की power k, x की power k is 0, this is anyway 0, right? So this implies that rk This implies that if commutative, okay, this implies that this. So if R is commutative, so this Rk is a Rx is a member of N, and XR is a member of N. This implies that if R is commutative, then N is an ideal in R. So option this is true. So this option is true. Okay. So I don't know whether so N need not be an ideal always. Okay, if only if it is commutative, then R is commutative. Okay, this then it is ideal. Okay, I think you got my point. I don't know. Yeah. I think you got my point, right? So what is the next thing I am going to do? So let if I and j be two ideal, if I and j are two ideal, so let I and j are two ideal of R. R is a ring, right? So what is I plus j? I plus j is small I plus small j, such that I inside I and j inside j. So this is an ideal? Is this is an ideal in R? Check, verify. I guess. What do you think? Will it be ideal? If yes, then prove that. If no, then also prove that. So this is very easy to prove. Suppose let A comma B are two member of I plus j. So some A will be some I1 plus j1, and B will be some I2 plus j2, right? I1 I2 inside I and j1 j2 inside j. I am not going to write. I am giving you just small idea. So what is A minus B? A minus B will be some I1 plus j1 minus I2 minus j2. Okay, you can write it as I1 minus I2 plus j1 minus j2. So this is an I1, this is in j1, sorry, this is in I, this is in j. This means that this is implies I plus j, this is inside I plus j. And also let R be an element of the ring R. So R dot I plus j will be Ri plus Rj. So Ri is a member of I and Rj is a member of j. This implies that this is a member of I plus j. So it's very easy to prove. Okay. Okay, so I plus j is an ideal. So I'm going to do some proposition here. What is that? Yeah. Let R be a ring with unity. Let R be a ring with unity, and suppose I be an ideal, of R. If I contains a unit, then I equals to R. This is the most this is a very useful result. Suppose you have R, you have a ring with unity, right? So if you have ring with unity and you have an ideal of this ring R, suppose I contains a unit, suppose I have a unit, I contains a unit, suppose I contains a unit, then I equals to the entire R. That means I will be the entire ring R. There is no other choice. If I contains one unit, then I will be the entire ring R. Okay, there is no other. How do we prove it? How do you prove? So I think the proof is very straightforward here. So let A be an unit, A be an unit, A be an unit, A be an unit in I, and I is an ideal in R, right? So if A is an unit, this implies that there exists an A inverse inside the ring R, such that A inverse this is equals to A inverse this is equals to 1, which is inside I, right? 1R, that means the unity. What is the unity? So since this element inside I, and this is inside R, so this implies that you can write it as this R dot I or I dot R. Okay, so this element is inside the ring R, right? So this implies that for every R inside R, R dot 1R, R, which is inside I, and this R is inside R, and this 1R is inside I, right? So this implies that this I is R, right? If A is an unit inside the ideal R, so what are the possible? See, I is an ideal and A is an unit which is in I. So if A is an unit, so there exists an A inverse inside R such that A inverse is equal to I, as is equal to 1, which is inside I. So A and A inverse, A into A inverse will be in I. So A is an element in I, and you have an element A inverse inside the ring R, such that this and this is going to be 1R. So and 1R is an element in I, right? Because see, this is an element in R, right? This 1R, no, this 1R is an element in, see, I is an ideal and you have an element in R here. So I dot R should be inside I. This 1R is inside I. Are you getting my point? A and A inverse. Suppose this, what is the definition of an ideal? So you must have A dot R should be inside I na, for ideal. See, this where this from R and this is from I. The similar case is where for A I am getting A, and for R I am getting A inverse, because A inverse is an element of R. So A inverse, this is an element, this is, what is that? This is 1R na, and this should be in I. That means this 1R should be in I. Are you getting my point? This is in I, right? For every element, if R is that, so see, this is a ring with unity, so R dot 1R will be R, which is inside I, of course. So this implies that for every element you can take, if you take any unit here, so you will get the I to be entire R. Okay, I think the proof is clear to everybody, right? Very easy proof, just some simple observation, nothing else is here. So from this I just want to ask one question here. I want ideals of q plus dot. What are the ideals of q plus dot? So you can use this result. So let I be an ideal of q. So every non-zero element is a unit here, right? Suppose I is 0. Suppose you want to include one extra element here. Suppose R is an element you just want to include here. In Q, every non-zero element is a unit. Every non-zero element is a unit. So R will be also an unit. So if I contains a unit, that implies that this will be entire Q. If I does not this will be, or I equals to 0. It cannot contain more than one element. If it contain more than one element, it will be entire Q. Okay. Suppose you have 0, you have added, and you have added one more element R. Since in Q every non-zero element is unit, so R is also is an unit. If it is unit, so I contains unit here. I contains unit here, right? If I contains unit, that will be entire Q. I just have the theorem, right? It contains unit. This is entire Q. So it has two ideal. Either it is 0 or it is Q. It has two ideal. This Q has exactly two ideal. Okay. So should I define maximal ideal? So the lecture will 1 hour 40 minutes, right? So let me define maximal ideal and the prime ideal. After that I will finish this lecture, I guess. Maximal ideal, prime ideal, and some examples. After that I will finish this lecture. Okay, just define what is maximal ideal. Maximal ideal. This white color is making disturbance here, so I think I should change the color. No, this color is also making. Let me this what is that? Yeah, let me work with that. Maximal ideal. First of all, my question is why it is called maximal. Why it is called maximal? Why it is not maximum? Can you say? See, so what is the difference between maximal and maximum? So we always has, if some element, if something is unique, then we say this is maximum, or if it is not unique, then you can say that this is maximal. It may not be unique. Okay, so maximal element must maybe there is more than one element which, okay, and maximum is unique. That's it. So anyways, this is my dot. So what is maximal ideal? Let R plus be a ring, R plus dot, let R be a ring, R be a ring, an ideal I, which is not actually not actually R, is a proper ideal, is called maximal ideal. It's called maximal ideal if it is not contained in any proper ideal. Of R, or you can say one thing, an ideal I of R is called, let me just write first, after that I will explain. It's called maximal if I is contained in J is contained in R for some ideal J. This implies that I equals to J or J equals to R. What is the meaning of that? Suppose you have two ideal, right? No, suppose you have an ideal. So how can you check for the ideal whether it is maximal or not? So maximal ideal you have to check. Suppose if you have an ideal I, so it should not contain in a proper ideal, right? See, I is contained in I is contained in R. This definitely have to satisfy, but it must not contain any proper ideal J, which is a proper ideal of R. Okay, this I should not contained in a proper ideal of R, right? If it is not contained in a proper ideal of R, right? Or another definition, or another way you can say, an ideal I of R is called maximal if I inside I is contained in J is contained in R for some ideal J. This implies then I equals to, if I is contained in J is contained in R, J is an ideal, then I is equal to J or J is equals to R. Okay, that means I should not contain in a proper ideal, right? Suppose for we'll see the various examples. So I should not contain in a proper ideal of R. That means I is the only proper ideal of R which is bigger than there should not have any ideal between I and R in the sense of the cardinality or the size. Okay, there should not be any ideal in between I and R. In between I and R, I is maximal if there should not have any ideal between I and R in the sense of size, right? That means I should not be inside J, contained inside J, right? So this is the definition of maximal ideal. If F is a field, okay, if F is a field, so what are the ideal, what are the maximal ideal, what are the ideal? So okay, so in the last I defined a theorem. If I contains a unit, then I equals to the entire ring R, right? So what are the if F is a field, so for the corollary, as a corollary you can say that if F is a field, this implies that F has only two ideal, 0 and F. There is no other ideal except 0 and F, right? Are you getting my point? F is a field, then F has only two ideal, 0 and F. Why? Because if F is a field, then every non-zero element is in unit. It's not it. So if every non-zero element is in unit, so if I is an ideal, it is contains 0 and some any unit A. If any element A, if A is a non-zero element, so A is an unit, so I contains a unit, that means I will be entire field R F. So it has only two ideal, F and 0, right? So from here, what can you say about the ideal? If F is a field, then what are the maximal ideals of F? If F is a field, if F is a field, this implies that 0 and F are only ideals. What are the maximal ideal? Is 0 is a maximal ideal? Yes, 0 is a maximal ideal. 0 is maximal. Because in between 0 and F there is no other ideal, and that contains 0. There is no other ideal I which contains 0 and which is an ideal of F. There is no other. Can you find any ideal here? There is no such ideal. So 0 is the maximal ideal here. 0 is maximal ideal, right? 0 is the maximal ideal here. So 0 is maximal ideal here, and 0, there is no ideal I in between. That means this has been squeezed between, or what is called sandwich between 0 and F. There is no such ideal, right? So that's why 0 is a maximal ideal. So in a field 0 is a maximal ideal. So what are the ideals? So suppose in example, suppose in Z, so 2Z and 4 in Z, 2Z and 4Z are ideal, right? So 4Z is contained in 2Z, right? And 2Z is contained in Z. So for the it is not maximal, that is max, and this is maximal, because you cannot find any ideal in between them. Can you find any ideal between 2Z and 4Z? No such ideal is here. So that's why this is a maximal ideal, this is a not maximal ideal, right? So 2Z is a maximal ideal in Z, but 4Z is not a maximal ideal in Z, right? Okay, let me define prime ideal. Prime. What is a prime number? First of all, what is a prime number? P is a prime number. What does it mean? That P has only two divisor. One is 1, another is P, right? P, this is P. P has prime number. In other words, you can say if AB divides P, this implies that if AB divides P, this implies that either A divides, if AB divides P, then either A divides P or what you can say is okay, so not AB, that P divides AB. If P divides AB, P divides AB, this implies that P divides either A or P divides B. Okay, this is the definition of prime number, right? In another words, if P divides AB, this implies that either P divides A or P divides B. Okay, This is the definition of prime number. So similarly here we can define for the prime ideal. Here I will define, suppose an ideal P, an ideal P, P is proper ideal is called a prime ideal. Prime ideal if AB inside P, this implies that A inside P or B inside P. Are you getting the definition? If an ideal P is a proper ideal, is called a prime ideal if A dot B means two element, AB in R. Okay, if AB inside P, this implies that either A inside P or B inside P. There is no other choice. This is the definition of prime ideal. Okay, two elements, actually two elements. This is dot. This implies if I give example, then it will be clear. So what are the examples? In Z, in Z, 0 is a prime ideal. Oh my god. Is a prime ideal. 0 is a prime ideal, right? Why 0 is a prime ideal? Because you take any element, A dot B is inside I means 0. This implies that either A equals to 0 or B equals to 0. Prime ideal. AB inside I, that means AB equals to 0. It's not it. That means this implies that either A inside 0, A equals to 0 or B equals to 0, right? And what is the another example? Okay, so is 0 is a maximal ideal? Is 0 is maximal in Z? Easy. Why? No. Easy. Why? Because 0 is contained in 2Z, is contained in Z. 2Z is here. In between them there is 2Z is here, which is proper. So it is not. So this is not maximal in Z. Right? It is not maximal ideal in Z. So one last question I am giving you, and I will end this lecture by this question, last question, right? So because my board is not working properly today. Yeah, question. Let me see the question. So okay, one question is here. So suppose that I be an ideal object. Let I be an ideal object. Then which of the following is or are true? Option number A, I is prime ideal object. Prime ideal in Z. Option number B, I is prime implies I is maximal. Implies I is maximal. Option number C, I is maximal implies I is prime. Option D is none of them. None of the above. Okay, what will be the right which one will be the, I'm giving you 2 minutes to think this question. I guess this should not take more than 2 minutes. Okay, which of the following is not true? Just think about it. Not so hard question. So okay, okay, the time is up. Okay, how can I proceed for that? See, first example is anyway false. I is prime ideal in Z. I is an ideal in Z. Then I is prime ideal in Z. Is it necessary? See, 4Z is an ideal in Z, and 4 is in 4Z. You are right. Does this imply? Okay. This implies that 2 into 2 inside 4Z. Does this imply? This is not 2 inside, sorry, 4Z. What is happening? No, na. So I is not a prime ideal, I think. No, it is not inside 4Z. See, 4z is an ideal, so I is an ideal, so 4 is an element of 4z, so 4 means 2 into 2 inside 4z. Does this imply that 2 inside 4z? No, 2 cannot be inside 4z, because 4z, what is 4z? 4, 0, 4 plus minus 4 plus minus 8 is multiple of 4, with 2 cannot be inside, so this is not a prime ideal, so this option is anyway false. For the second option, so if I is a prime ideal, does this imply I is maximal ideal? No, of course no. We have just example. What is the example? 0. 0 is a prime ideal. Why? Because 0 is prime ideal, because a b inside I 0, that means a is 0, b is 0. But 0 is not a maximal ideal. No. Why? No, because 0 is inside 2z, is inside z. Are you getting my point? So second option is also false. If it is 0 is prime ideal in z, this is for a, this is for b, this is for b, right? 0 is prime, this boat is really not working. I don't know what is happening. I think you should have get the point. You get the point, right? Zero is prime in Z, but not maximal in Z, because as 0 is contained in, anyway 4z is contained in Z. There is one more, so this is anyway false. And the third option, I is maximal, then I is prime. So for the C option you have to work, and this option will be true. This option will be true. Why this will be true? I am precisely, you have to do precise, right? So I don't know why my board is not working today, so I'll have to finish this lecture, I guess. Anyways, so let's try it. Okay, see, keep changing, right? So suppose I is, if in Z, if I is a maximal ideal, I have to show I is a prime ideal. Suppose H be an ideal, let H be any ideal, H be any ideal of Z. This implies that H is hovering of Z. This implies that H is a subgroup of Z plus subgroup of Z plus, right? This implies that H is some mz for m belongs to, for some m belongs to Z, because all the subgroups is of the type mz, in group theory course we learned that every subgroup of Z is of the form mz. Okay, so all the ideals, ideal is a subgroup, right? So all the ideals of z plus dot looks like mz, m belongs to z, right? My question is when mz is maximal? If it is maximal if and only if m is prime, right? Why? Because as you could take as in the short, as see tangent is in 2z, is contained in 2z. See here, tangent is contained in 2z, right? It is also contained in 5z. It is also contained in 5z, right? Mz is contained in nz if and only if n divides m. Just let me just mz is contained in nz if and only if n divides m. It's not it, n divides m, right? So tangent is contained in 2z if 2 divides tangent. So tangent is contained in 2z. 5 divides 10, so tangent is contained in 5z, right? So this is the reason for the maximality. Suppose you have 3z. Can there be any other I which is contained in z? No, it cannot be. There will not be anything in between 3z and z. If 3z is not contained in 2z, 3z is not contained in 2z, 3z is not contained in 2z, right? So 3z is only contained in z, so 3z is maximal. 3z is maximal. Are you getting my point? So m is a maximal ideal if and only if a is a prime number. So it is clear, right? So pz is a maximal ideal for p prime. So pz is maximal for p prime. For p prime, pz is the maximal ideal. Pz is the maximal ideal, right? Is pz is a prime ideal? Pz is a maximal ideal. So if pz is a maximal ideal, does this implies that pz is prime? This is the question. The third, what is the third? If I is maximal, does this imply I is prime? If I is maximal, does this imply I is prime? So here pz is maximal. Does this imply pz is prime? Yes. Why? Let me just which color I should take, which color? All the colors has been I don't know which color I should take. Anyways, there are so many colors. Yes. Okay. Oh, this is really not working. Let me see this. Let A be inside pz. Pz is maximal ideal. whether from pz, if pz is prime, then a inside pz or b inside pz. What does it mean? This means that ab will be some pk, for some k inside this z, right? ab inside ab equals to pk, right? ab will be some pk for some k. If a comma b inside pz, if a comma b, not a into b, okay, a comma b inside pz, does this imply that a dot b ab inside pz? No, it cannot imply. Suppose p, I am taking p to be 5 is a prime number, right? So I am taking, suppose 5z. Suppose see 5 inside 5z and okay, a comma b inside pz. Does this imply that ab inside pz? Okay, I have taken 5z. Suppose I have taken 5z. So 5 is an element in 5z and 10 is an element in 5z, right? Thus ab is 10z. 50z. Okay, does this imply that 50 inside all the multiples of acha 5 into 2, 5 inside 5z, yeah, that's fine. And 10 inside also 5z, 5 to the 10, but 5 into 10 is 50. So 50 inside, yeah, 50 will be inside 5z, right? So this is a prime ideal. Suppose 5z is a prime ideal, right? So if 5z is a prime ideal, so if ab inside z, if a comma b inside pz, it implies that ab does not imply a into b is not inside pz. But this is not this is violating the fact here. A inside 5z, 5 inside 5z is 0, 5. 5z means 0, 5, 10, 15, plus minus. So 5 is in and 10 inside 5z. So 5 into 10. So 5 into 10 is 50. 50 inside, yeah, of course 50 will be inside. I mean 5, 10, 50 will be inside pz. Suppose that in 3z, 3 inside 3z, 6, 18 will be in 3z. All the multiples of 3, yeah, of course. I guess this implies that ab inside pz. So this implies that ab inside pz. So this is false. So if a or b, if ab inside pz, this implies that either a is inside pz and b is inside pz. So suppose ab inside pz, this implies that a inside pz or b inside pz. See, ab inside pz, that means AB inside PZ, that means it will be some multiple of P, right? Suppose for example 15 inside PZ, 15 inside 5Z. So 3 into 5 inside 5Z, this implies that 5 inside 5Z. So that's same here. So if AB inside PZ, that AB will be some multiple of P, some PK. So it essentially implies that either A is inside, either A will be some PK or B will be some. So P is fixed here, right? So P K will vary. So this implies that if A is inside PZ, this implies that AB inside PZ or A inside PZ or B inside PZ. So what I was thinking here is, I guess, not AB inside PZ. AB does not inside PZ. Who told? No, A comma B inside PZ. So suppose 5 is inside 5Z and 10 is also inside 5Z. So does this imply that 50 is not inside PZ? No. So anyways, so this is PZ is a prime ideal. So this option is correct. Okay. So all the maximal ideals of Z's are prime ideal actually. So I think this is for today. We'll discuss more questions in the next lecture. Okay. It's been 2:19 a.m. so I think I should stop now, and the lecture has been already 2 hours 18-19 minutes. So let me finish with that, and we'll meet in the next lecture. Okay, thank you. Also my board is not, I don't know why I don't know why. Thanks for watching, right? Okay, bye bye.